going out now. So we're going over to work with Jeff. We're going to do subglacial lakes, and we'll switch in about 2 hours. We're actually back on schedule.
So do they need to bring?
You need to get your clothes.
Okay. So when you guys take the stuff out, right?
Yeah, well, you know what, let them take the whole bag, but when you come back, this is gonna be confusing. We're gonna actually switch over there because we're gonna do a whole group shot. So you guys are gonna wear Carhartts like the support people. They'll still have on their big reds, and we'll do a group shot of School of Ice out in front of the ice core facility door. So there'll be a little confusion as we change and stuff like that. Then they'll give you the clothing and the bag, and you'll bring the bag back. You guys tell them what number your bag is, because it's not actually on the bag. Okay? All right, so just go grab your bag and finish your dressing up there, and have fun.
That's for
Am I taking them to the freezer?
Huh?
Am I taking them to the freezer?
Yeah, take them to the
So when you
freezer.
take your bag, just remember your number. Okay.
Be careful out there.
You want to make sure you have them to the back of
Okay. Yeah, go ahead and start. What are you doing here?
I'm Matt, as she said. I'm really thrilled to be here because I'm a new professor and you've all been teaching a lot longer than I have, so I have more to learn than you do. Hopefully I'll teach you a few things, but I'm excited to just hang out for the next few hours and go with you all. So I'll be talking about a different type of drilling, one of the 3 legs of the USIceDrilling program. The subglacial access leg is a little newer than the others, so we try and advertise ourselves a little bit more. So this is actually a picture of a floor of an Antarctic subglacial lake. We'll talk about that more in a bit. As Lee said, I'm at Colorado School of Mines. You can find me, you can email me, but probably quicker to find me on Twitter and Instagram at USIceDrilling. So who am I? Why am I here? You can't really see the picture, but that's me in case you forget what my face looks like. That's me in front of Russell Glacier in Greenland this past May. You've probably read about Greenland a little bit in the news over the past few months and how much it's been melting. It was really impressive. I was flying around in an airplane. It was really impressive how much early season melt there was this year. I'm a physical glaciologist. I try and use physics to understand how ice sheets move and how ice sheets change and how they interact with different components of the Earth system. I basically am willing to use observations from anywhere, whether it's beneath the ice, from the ice sheet surface, from the air, or from a satellite. And I try and tie these observations with my colleagues that work in other fields, geochemists, microbiologists, modelers, to answer these scientific questions that intrigue me. For the past 4 months, I've been an assistant professor at the Colorado School of Mines. Before that, I was at Dartmouth College for my undergraduate and my master's. So I've been hearing about IDPO. That's their whole name. Their name changes every few years. So I've been hearing about the ice core drilling program since I was just a little baby in college. Did my PhD at Scripps Institution of Oceanography in San Diego. I did some postdoc work at Stanford University, which is just a long way of saying I've lived in every time zone, which seems to be a theme for academics these days. What I hope to take away, I like showing the last slide first, so you know what you're going to get into. Hopefully you get a little bit about how glaciers and ice sheets work and how they impact and are impacted by other Earth systems. How we use scientific drilling to investigate modern processes. You're going to be talking a lot about paleoclimate. I'm looking at what the ice sheets are doing today. And these things really dovetail nicely because we need to know about both to really understand how the ice sheets work. And really, I think the most important part, because you all talk with students that tend to be younger than me, so you're the ones who are getting the students excited, and hopefully sending them to me. that this is a really exciting field. There aren't many fields of science where you're making kind of first order discoveries. The stuff I'm going to be talking about, 2005, didn't exist. We didn't know about it. Well, it existed, we just didn't know about it. We didn't have observations to constrain these problems. And so every year, we're making new discoveries. The first time we accessed one of these subglacial lakes and got into the subglacial environment in Antarctica was 2014, 5 years ago. The second time we did it was this year. So this is really exciting discovery-based science, and that's what got me into it. That's what gets a lot of students into it, so I think it's really cool. And I hope to convey a little bit of that through the next 30 minutes or so. Are any of you sticker people?
Yeah,
Stickers?
I am.
Okay. Well, I have a big stack of stickers. This is what NASA gives you when you deploy to an ice sheet with NASA. So if you like stickers,
Do you want me to pass them out for you?
yeah, sure. Please take them off my hands. That's why I came home from Greenland. The next thing about NASA is it is illegal for them to produce a sticker with no educational information on it. So the back has the back of NASA stickers always has great information for you. Okay. So some quick background. This is the first day of the School of Ice. So I actually don't really know what you covered this morning with ice cores. Did you learn what a glacier is? What sets a glacier apart from any other part of the cryosphere? Great. So I look at this picture, I'm like, oh, cool, that's a glacier. You could trust me, you could not trust me. What do you think actually makes this a glacier? There are two things. What's the first thing you said?
Mobile.
Yes, it's flowing. It has to flow under its own weight. So that means it's thick enough that's gravitationally unstable is what we say. It just means it's too tall and it wants to flow high. There's one other thing. What's a glacier made of?
Water. Ice.
Ice. How does that ice form? Is it frozen? Is a frozen lake a glacier? Accumulation. The snow has to, a glacier needs to be made of snow. So you dump snow in one spot, it piles up over time, it starts compressing, turns into ice, and then it starts flowing. So that's all a glacier is. Ice that formed through the compression of snow, and it flows under its own weight. I think about the physics of glaciers and how glaciers move, so we're really going to be focusing on number 2. And there are actually 2 ways a glacier moves, not just through internal deformation, which is it flowing because it's tall, but it can also slip over the bed. And you can just think about that as it's sliding. There can be water in the bed, water's wet, it's slippery, ice, just like us, slip right over water. So if you think about these 2 processes, and this is like, I'm trying to compress like 2 weeks worth of glaciology into a slide right here. So if you think about these 2 processes of how glaciers move, what do you think internal deformation depends on? I've kind of hinted at a couple of things.
Slope.
The slope, surface slope and bed slope. So if it's a steeper slope, is it going to move faster or slower? Faster. What else does it depend on? Thickness. It flows under its own weight. Thicker ice will flow faster. It also depends on temperature. That's not one I typically expect people to get, but warmer ice. So ice just needs to be below 0. It can be as cold as -60, -80 degrees. Warmer ice is going to deform faster. What about basal slip? What do you think that depends on?
Think of like bedrock friction resistance you get out for that slide.
Yeah. What's underneath? So it could be sediments, it could be bedrock, it could be rough. Roughness is really important. What's the other thing that can reduce friction really effectively?
Fluid.
Fluid. You got everything. And so it turns out that fluid is really the critical part of the recipe here. So if you get more water, there's less friction, it'll slide faster. So if you look at, and feel free to stop me whenever, because this is a lot of information. When you look at a velocity map of Antarctica or any ice sheet, it's a little washed out here. The velocity scale goes from basically 0 meters per year up to about 3 kilometers per year. So that's flowing at about 50 feet per day or so in the purples, and well, what's coming out is black. And basically when you look at this, you can see what looks like a slow motion river system on any other continent. Up in the highlands in the central part of East Antarctica, where you have about 4,000 meters of ice, you have slow moving glaciers. These kind of coalesce as they flow down slope, not unlike up in the mountains here. You have small creeks that then turn into bigger rivers. They coalesce into these really fast-moving plugs of ice we call ice streams. And these narrow little features here that you can see all along the edges of the continent are responsible for discharging 90% of the ice from Antarctica into the ocean. And so that's where we're losing mass, is in an ice stream. So if we want to understand the fate of the Antarctic ice sheet and how much ice it's going to put into the ocean, we need to understand these narrow features, ice streams. If you were to hypothesize where on the continent flow is more driven by internal deformation versus basal slip, well, let's just say internal deformation to start, where do you think that's the primary mode of ice transport? We talked about what depends on slope, thickness, ice temperature. What was that? This side, this side. So this is East Antarctica, this is West Antarctica. Where in West Antarctica? Do we think that these ice streams are moving mostly by internal deformation? So I actually don't have ice thickness on here, but I'll tell you that this is really thick ice, about 4,000 meters, and ice streams tend to be about 1,000 meters. East Antarctica, central spot of East Antarctica up near the divide is mainly where you get ice deformation. Ice deformation is typically a slow process. It's what we think of when someone says, you're moving at a glacial pace. That's internal deformation. Basal slip is what is responsible for all these ice streams. So just like we have the ice streams coalescing into these rivers of ice called ice streams. Wow, that was circular. We have the slow-moving ice coalescing into faster-moving ice, forming ice streams. Underneath, we have a hydrology system that's doing the same thing. And so you're creating small little pockets of water, little creeks up in the highlands beneath the ice. And then that all funnels into a bigger river. And that's what's letting this ice flow quickly.
That picture on the left, where is that taken on the map?
One of these tiny little glaciers coming out of the mountains down there. So this was actually taken from the plane ride from Christchurch, New Zealand down to McMurdo Station. And that flight takes you right along here. So it's really one of the spectacular flights. Polar Trek is a great program. You should all go down to Polar Trek. So that's basically the background. We care about ice streams. Because we care about ice streams, we care about water beneath the ice, because that's what allows the ice streams to flow quickly.
Matt, can I ask a question?
Of course.
I couldn't quite hear what you said. You said basal flip? What did you say?
Slip.
Slip.
So we use that as a catch-all term because there are lots of processes that go on beneath the glacier. You can have this sliding over the bed that's accommodated by an actual layer of water. You can also have the sediments under the bed, wet sediments. They're actually actively deforming, and because those are deforming, they're taking the ice above it along with them.
Thanks.
So it's just, I think I had it in quotes because it's like this esoteric term that doesn't really mean anything.
Okay.
So we've been thinking about these problems for a long time in mountain glaciers. So at least 250 years now. So here's a little quote from a Swiss naturalist in the late 18th century, where he basically says that almost all glaciers up in the Swiss Alps have streams of water that flow beneath them, and that's what's really supporting the ice and allowing it to flow down valley. And the reason we know a lot about this, and we've been thinking about these problems for 250 years, is because you can walk up to these glaciers and see the systems. So you can't see it here, but there's a little tunnel beneath this glacier and a gigantic river coming out from beneath it. This is Fox Glacier in New Zealand. And so you see things like this, as a naturalist would do in the late 1700s, and you'd be like, what's happening here? And so you take some measurements and you start to piece this story together. We've been working on this for about 250 years, so we have a pretty in-depth mental model of what these water systems on a mountain glacier look like. You have these superglacial systems, so on top of the glacier, where you get lakes and rivers and streams and mushy snow, what have you. This all enters an englacial system, so plumbing within the glacier itself, either through crevasses or what we call moulins, which are basically big shafts that the water carve out themselves, so just the act of the water flowing carves that. That gets it down into a subglacial system, where it can go into a lot of different types of water systems, which we'll talk about in a second, and ultimately it all flows out into the Foreland Basin as you typically meander streams over these outwash plains. For scale, this is about a 10-meter tall rapid. This is actually in like our primary glacier textbook, the White Rapid. So we can take observations of the surface, but then we need to model what's going on at the bed. And so we've come up over the past 250 years, all these different types of models, and I'm basically going to separate this onto the two halves. On the left side, we have what we call a channelized model, or an efficient system, which is basically just like a pipe beneath the glacier. And that's what I saw at Fox Glacier in that picture. On the other hand, we have these slow, inefficient systems that are these thin films or connected cavities, where water flows a lot slower through these systems. If you try and shove more water into one of these systems, what do you think happens to the water pressure? It goes way up. And so what will that do to the ice velocity? It'll also increase. So on the right side, when we have more water, we have higher velocities. What about on the channelized systems? If you pump more water through a pipe, do you think that's going to increase or decrease water pressure? It actually decreases the water pressure because it can actually melt out a larger channel. Just the friction of that water moving through the ice will make a wider aperture for it to flow through and decrease water pressure. What happens to ice velocity? More water in a channelized system.
Should it speed up the ice also because there's more water over there, or?
But the water pressure goes down, and that's the thing that really drives velocity. So you need the high water pressures to decrease friction at the bed. So more water in a channelized system slows down. And so these systems that are invisible to us, they're beneath hundreds of feet of ice, really are critical to understanding what water is going to do to a glacier. So here's kind of mathematically how we phrase this. In a distributed system, increased discharge Q is proportional to water pressure, whereas in a channelized system, increased discharge is inversely proportional to water pressure. And so this is about 250 years worth of glacial hydrology work. Cool. But those are mountain glaciers. I'm not here to talk about mountain glaciers. We care about these because they can lead to huge disasters for human infrastructure. This is Iceland, where a subglacial lake in Iceland flooded, formed one of these channelized systems, and basically became this gigantic pipe to drain the entire lake, took out this entire road. We call this a jökull, which is an Icelandic word for subglacial outlook burst flood. We have them in Iceland, we have them in Juneau, Alaska, we have them in Switzerland. These things, we have them in high mountain Asia. They can be really disastrous, take out entire villages. So we think about these things a lot for mountain glaciers. We've been thinking about subglacial hydrology and hydrology in general in Greenland for almost as long, about 150 years now. This all started with Dr. Henry Brink in his original exploration of Greenland, where he talked about the subglacial streams that he could see coming out at the front of the glacier. So here's a sediment plume, which from that we infer that there's being water injected at the bed. And he says in 1877 this can be considered as lifting the ice to facilitate it gliding towards the sea. And in the appendix of his book, there's actually this really interesting passage where he talks about talking to the native Greenlandic people who actually tied the entire system together. They saw melting upstream, flowing down into these moulins, these shafts that can connect to the subglacial system. That flows out, and it increased, they knew that it increased iceberg discharge because they were fishing in the water. They knew not to go fishing when there was a lot of melt going on the surface. So I say we've been thinking about this for 150 years in Greenland. Native knowledge suggests we've been thinking about it way longer. That's Greenland. We have people, we have lots of observations over on a century scale. What about Antarctica? You can just go and see it in Greenland. Oh, I gave you a cartoon. Forgot about this. So we can make little cartoons for mental models. So we have these lakes on the surface, which you can see here. These drain through moulins, get to the bed. They enhance basal lubrication, leads to ice acceleration. In Antarctica, things are a little different. Here's that picture of Greenland, lake on the surface. Here's a picture I took of one of the warmest parts of Antarctica. How much surface water did you see? Not much. For satellites, we can actually measure the mean melt duration over the surface of Antarctica. And you see over most of the continent, and especially the grounded continent inside the black line, 0 meltings, maybe a few in a hot year. So we don't have all this water from the surface getting to the bed. So the hydrology system is going to be totally different because it's being driven by a different source of water. So if we take this cartoon of Greenland that we have, none of this stuff on top is in this system. It's only any water that's created in situ, so at the ice bed interface itself. So we have one input into the subglacial water system in Antarctica, and you might say, but Matt, ice is cold, Antarctica is cold. Why is there water beneath the ice sheet? Any ideas why?
Compression?
Compression of what?
The weight of the ice is heating the lowest levels of it melts, maybe?
So
Higher pressure.
So higher pressure doesn't actually melt it, it makes it easier to melt. Because if you look, I'll show a phase diagram of water in a second, but the melting temperature goes down, and so you have a few degrees less you have to warm the ice to melt it. But you still need heat to melt the ice. Volcanoes. So if you kind of generalize that, heat from the earth, geothermal heat. And so even not in a volcanic regime, you have heat coming up from the earth. We have radioactive elements in the crust. That decays, creates heat, and you have heat coming up. And we have actually in West Antarctica, it's a rift system. And so that's like Hawaii, Iceland, things like that, where you actually have a ton of heat pumping up from the earth. What else might generate heat? We've talked about one thing. What's that? So we don't have water yet. Yes, but that's not underneath the grounded ice.
Latent heat.
So if you have phase changes, yeah, you can generate more heat. You can get positive feedback loops in the system. What about friction? We've been talking about that. So once you start moving the ice a little bit, you can get more heat into the system through just the ice rubbing on the ground. There's one more that we call strain heating. So imagine taking a piece of metal, bending it back and forth really quickly, and then you touch that little bend right there. It's really warm to the point you can actually burn yourself. That's just molecules inside the metal itself rubbing against each other. We call that strain heating. Same thing happens in an ice sheet, where you have, near the bed, you have this big velocity gradient. And so those ice molecules are grinding against each other, creating heat. So you have 3 inputs of heat. You have overburden pressure, which we talked about. Here's that phase diagram. So usually you're melting ice at 0 degrees at about atmospheric pressure. As pressure goes up, that melting temperature goes down. That's weird. Water's really weird when it comes to materials on Earth. Very unique. And then there's one more, and that's the ice actually the heat can't escape. Ice is a great insulator. And so you can't conduct this heat away. It stays at the ice bed interface once you create it. And people that go winter camping or who have taken a winter safety course all know this intuitively, because if you get stuck out in the middle of nowhere, everything goes to hell. What do? You dig a trench and you sleep in your trench, because you're going to be shielded from wind, but also it's going to be warmer down there. And so this is me in Antarctica in a survival trench. I actually slept down there in my first season for a night. It was a fun evening. So you can't see red at all on this slide, but can we measure these heat sources? How do we know about this? How do we use this information? Do we think it's easy to measure the heat sources beneath thousands of feet of ice? Don't all shout at once.
Sure you did as your coring.
You do as you're coring that, so we have these spot measurements. So that's actually one of the best places we know, say, geothermal heat beneath Antarctica.
Is that any sort of satellite sensory equipment that could pick this up?
We can infer it from how seismic waves travel through the Earth down there, but that's a very coarse measurement. We would like to know it on finer scales. Any ideas? The answer is we don't really observe it. We model the whole thing. And so we have our thermodynamic models. We can make guesses at how much heat is coming from the Earth based on our guesses about geology, but these really are just guesses. It's all been covered by ice for 42 million years, so we don't really know. But we throw into our model, and we say it's right. And then we can estimate how much water is being produced locally at the ice bed interface across the continent. And that's about 65 gigatons per year. Do any of you have some sort of intuition about how much water that is? It's a meaningless unit that none of us have experienced, but it's enough to fill Lake Erie every 7 years. So it's not an insignificant amount of water, but it's not a ton of water. I mean, this is orders of magnitude less than go through the hydrosphere in North America per year. So you have some water, not too much water, and so that's your input to the entire system. That's it.
Can I ask a quick question?
Of course.
On the map here? On the western Antarctica, it's warmer.
Yep.
You mentioned some tectonic reasons for that, higher heat flow in the
Yep.
subsystem geothermal. Why the rim around Antarctica on the eastern side? It's like there's a halo of heat all the way around, yeah.
So that's what you were talking about. That's the ocean coming in and providing the heat to melt it. So a lot of these places are floating ice shelves. And then you have the highest velocities along the fringe, so you have the most friction. So that's why it's red on the grounded side. Man, you all know about ice shelves already? That's great. What a day. So where does the water go? So we didn't really have large-scale observations in Antarctica until the 60s. So there's about 50 years of science we're talking about. And this was one of the first thing the first data we collected in Antarctica on any sort of large scale was airborne radar. And so airborne radar, all you're doing is sending out a pulse of energy, and you're listening for what comes back. And what comes back actually almost looks like an X-ray of the ice sheet. The radar energy penetrates the ice. It'll scatter back off of layers in the ice, which is, we use that for ice coring actually. It's the same sort of layers you see in radar. And then most of the energy comes back from the bedrock. So that ice bed interface reflects a lot of that energy. And depending on what type of interface that is, it'll send back more or less energy. So if you have rocks or rough sediment, it'll actually scatter a lot of the energy away, and so you get a dim return. Water is like a mirror to radar. And so you shoot a radar pulse at a lake, it can blow up your detector, it's so strong coming back. And so our first observations in Antarctica with airborne radar sounding, we started to get these weird features that look like mirrors. And so from these first observations, I know it's a beautiful radargram from the 60s. From these first observations, we already had some sort of inkling that there were lakes underneath here, 4,000 meters of ice. 13,000 feet, as tall as these mountains. Then we started getting better radars, and you can start to make out these features a little bit better. We got even better radars in the early 2000s, thanks in part to a lot of Department of Defense funding. We use radars to see missiles. That's the primary reason we build radars in America. We just kind of steal their knowledge and apply it to glaciology. You can see the beautiful layers, and then you see right here we have this flat, bright return, and we interpret that as a lake. And then here's pretty much the canonical image we show when we talk about subglacial lakes. Flat and bright, usually in some sort of depression. And so this is a water-filled cavity, a couple kilometers long, underneath a kilometer and a half of ice. With all the radar data we've collected, we can map it out across Antarctica, and you can't see it again, but generally there are red dots all over these slow-moving parts in the interior. And it turns out that we actually started coring one of these back in the late 80s. The Russians did it at Vostok Station, now the location of Vostok Subglacial Lake. When they started coring, they actually didn't know it was a subglacial lake. It was just this nice flat spot that they were like, this could be good for a camp. And then later, when we started doing geophysics, we saw that there was probably water down there. So these are in the interior, slow-moving ice. That's not what I said I was interested in. I want to know about the fast-moving ice and what water is doing down there. Why might people be interested in these sorts of lakes that are kind of in these bedrock hollows beneath that ice sheet?
Freshwater resource.
Freshwater resource. So Vostok Subglacial Lake is the 5th biggest freshwater body on Earth. So yeah, you could use these for drinking water. I'm not sure you would want to.
Well, how long do you think it'll be till we get a bottle of that for on the shelf someplace, right?
So with Vostok, they use kerosene as their drill fluid. So they actually haven't directly accessed the lake yet. For cleanliness reasons, we don't want to contaminate this environment. Why don't we want to contaminate it?
Well, I guess it's a record because it's been uncontaminated for hundreds of thousands of years, millions of years.
Millions of years.
That you could use it as a proxy for paleoclimate.
You can use it as a proxy for past life. You can use it as a proxy for paleoclimate. I mean, this is an incredibly unique evolutionary environment. This has been cut off from the world for millions of years. So the microbiologists are really interested in it. Some people think you might find fish in it. That's far-fetched. And then there are sediments accumulating in here. And again, paleoclimate, you can core these sediments and get a sense of what the climate has been doing over these millions of years. The answers, if you could read it, are also just on the slide. So when kind of the mental model for these lakes up in the highlands, up in bedrock-controlled lakes, it's like a lake up in the mountains here, or a great lake in the Vostok case. You know, most of these are small little water bodies in a granite bed, or sitting on top of a granite bed in a basin. There's another reason we were interested in these. In the 60s, there were some proposals to store nuclear waste in Antarctica, and the way that would work is you put the nuclear waste on top of the ice sheet, and at that point the ice sheet was just an ice cube sitting on rock. Didn't do anything. The nuclear waste would melt itself down to the bottom, and then it would sit there. At that point, we didn't know there was water beneath it, and this is actually from the first big paper about subglacial lakes. The practical need for knowledge of conditions at the base of the Antarctic ice sheet has been given special emphasis by a recent proposal for dumping radioactive waste on the ice sheet. So if there's water moving around, or even water stored there, you can contaminate this entire water system really quickly. That water then flows out into the ocean, and you've done a terrible job of storing your nuclear waste. So again, Department of Defense comes right back into this story. We also knew that there had to be some flow systems of water. It wasn't just stored in these lakes. And that's because if you look at this velocity map on the left, you have these ice streams of high velocity. But if you go through your thermodynamic models, some of these areas of fast flow actually correspond to freezing. It's thin ice, the heat can conduct away really quickly, and you should be freezing bed water at the bed onto the base of the ice stream. And so to sustain this fast flow, we knew you had to get water from where you're generating it up here to where the ice is still flowing quickly downstream. But we just thought this was steady state. You know, there's Antarctica, everything's slow, nothing's changing. But if you have fast flow and you have water moving through the system, we're likely in one of these distributed regimes where more water equals more velocity. We were on the left side of this plot in terms of our subglacial water system. You were sending this water downstream, it would slow down the glacier. So we had some questions about these systems. Will the system ever change? On what sorts of timescales? And kind of thought hundreds, thousands of years these systems would change. Pretty boring for someone interested in modern processes. And so kind of to summarize what we thought about pre-2005, 15 years ago, we had these steady state transport of water to maintain ice flow, high pressure distributed systems, potential for change on long term, doesn't really intrigue me, and potentially this could impact geology. You have moving water, it could move sediments around, what have you, so the geologists and the geomorphologists were interested. We have storage of water in subglacial lakes. These are bedrock controlled basins with long residence times. They could outburst if you change the ice sheet significantly, but again, that's like tens of thousands, hundreds of thousands of years. They're of interest specifically because they're isolated. Sediment traps, evolutionary biology, and it's a bad idea for nuclear waste storage. Then we started to get better tools for observing Antarctica, namely satellite missions that could actually observe down to the Antarctic latitudes. And we started to see really funny things. And so this is just a plot of surface elevation change, or surface elevation from 1995 to 2004, 10 years, over this one spot, L1. And what you see is that through time, all of a sudden, over the course of about 2 years, the surface dropped by about 4 meters. We don't expect things like that to happen in Antarctica. That was curious. If you look at some spots downstream, say U1, surface goes up by a little bit. U2 went up by even more, and U3, it went up by about 2 meters again. And so these were correlated changes in height over these small areas, and that was weird, unexpected for sure. And basically through the process of elimination more than anything else, we developed this model that these were probably changes at the base of the ice. Small little ponds of water flooding out, moving downstream. So the idea is you have this subglacial lake here, it's filled, it starts draining water, that brings the entire ice column down above it. So that's why you get this drawdown of U1. And that water flows downstream, fills up ponds downstream, and basically hydraulically jacks the ice column up. And so we have this idea of connected water movement in Antarctica beneath the ice. We started to have better tools, so that was a radar altimetry mission that was launched in 1992. We moved on to the ISAT mission, which was a laser altimeter, much finer resolution, launched in 2003, and we can map these big height ranges across most of the continent. And you have these bullseyes, again, of large height changes. We zoom into just this one location here. This is the elevation change from 2003 to 2009, from about negative 10 meters, so 30 feet of height change, up to about 1 meter, 3 feet. And you see in this area, the height fell by about 30 feet, whereas everywhere around it was going up by about 3 feet. If we look at just one line of data here, colors are now time, and you can see that we're in the surface basin, and the height of the surface basin drops by about 30 feet. If you track this in a time series like we did on the last plot, you can see that this area dropped. This is height change in meters averaged across the entire area. You drop on average about 6 meters, 20 feet over the course of 2 years, and then it fills right back up. And that's entirely consistent with what we expected a subglacial lake to do. Drains out its water, it keeps collecting water from upstream, and it refills. You have this cyclic subglacial lake drainage event. This was new 12 years ago. We can model where we think water should flow, and sure enough, if you look at hydropotential, which is the combination of bed topography and where the pressure of the ice above it is driving water, The hydropotential lows are exactly where we were finding these features that were interpreted as subglacial lakes. And so we're starting to tie this story together from a couple different lines of evidence that, yeah, this is probably water flowing beneath the ice sheet and changing on an annual time scales, or in some cases even less than a year. Here's a little movie of this that NASA made. So you have these two lakes. The upper lake is going to drain into the lower lake, and you'll see the entire ice column above the upper lake go down, and the lower lake go up. Thanks, NASA. That's what your taxpayer money goes to. If you map where these lakes are across the entire continent, they're almost entirely situated under fast flow. So now the light bulbs are going off in my head. This could be an important thing to keep an eye on. You have water moving underneath where the ice is flowing quickly. So you have this coupling here where these subglacial lakes can then change ice velocity of ice streams. Ice streams are the things we care about, or I care about. And so these become something really intriguing. So they're distributed throughout Antarctica, located in regions of ice flow, with inferred changes of water volume up to 5 cubic kilometers. So just one of these lakes represents a significant fraction of all the water created in 1 year in Antarctica. If you fly over these with radar, however, they look very different from the lakes we were seeing before. Up here, you have some of those flat, bright reflectors. Down here, underneath where you get these height changes on the surface, you don't see those flat, bright reflectors. From that, we know something is fundamentally different about the subglacial system in these locations. It's not one of these bedrock-controlled lakes anymore. We can create new hypotheses. In this case, we think they're thin water cavities on sediment. But this is where the geophysics ends. We can't really do better than this. And so how do we test this sort of hypothesis? Any ideas? Drill into it.
It's gonna cost a lot, but
We need to go explore.
analogs.
And so that's exactly what we did with the Wizard project in 2014. Drilled through half a mile of ice, trying to see if this was in fact a water body beneath the ice sheet. This was an untested hypothesis. So this was 5 years ago. Sure enough, we drill into it, we get about 4 feet of water. We see a lot of sediments on the bed. Thin water cavity on wet sediments. That's pretty cool. We developed a hypothesis from our remote observations. We went and tested the hypothesis, and it was consistent with our hypothesis. In terms of our mental model, this is an entirely different subglacial system. I think about this more like a wetland. The whole thing's marshy, but we have these locations where we have a little bit more water. And those are the places where we can see it filling and draining. And then we can use those locations, because we can see it on the surface, to then interpret the rest of the system. Why else might we be interested in these little ponds? What happens in wetlands? We have a lot of biologic activity, or low levels of biologic activity. A lot of biologic activity. So the microbiologists were really interested in these. And sure enough, if we took samples from this lake, and the rates of microbial activity were through the roof, like way higher than anyone expected. And if you kind of expand that, I mean, this is one lake we drilled, which is the best we can do. You take that and you multiply it by the surface area, or well, the area beneath the ice sheet, and you get these incredibly high rates of carbon turnover. So this could be a significant player in the global carbon system, which is what drove our next project, which was the Salsa project, where we drilled this past January into a different subglacial lake about 50 miles away. And sure enough, we'll run through this video again, I think. Sure enough, we see this mucky water column. You can't see anything. Entirely turbid until you get about a foot away from the bed, and then you can finally start making out what the bed looks like. And so that, again, is consistent with this mental model that there's a big marshy wetland environment. If you sit and focus your camera just 6 inches from the bed, you can get these beautiful pictures of what the bed looks like. We took some samples, we took sediment cores, as well as water samples and what have you, and you can pull out these amazingly diverse rocks, little pebbles from the cores. I have a little sample of the subglacial mud here if you want to look at it. But we're still working through this. This was January 2019. And so we don't know what we're going to find here. We know it's kind of a wetland environment, but there's a ton to learn about how this is different from the last lake, how it's the same as the last lake. We're still working through all of this. But in general, we can start forming this cartoon of what we think subglacial Antarctica looks like, where we have these lakes within subglacial valleys, bedrock driven, isolated, a lot of interesting science to be done there. And then as you move downstream, you get onto these sediment packages where you have these lake cavities and canals kind of moving around in these distributed systems, interconnected lakes, and finally all of this flows out into the Southern Ocean. So why do we care? What does a variable water system in Antarctica mean for us as scientists, as a community? I've been talking about one reason it matters. Was that? Rate of flow.
Yeah.
So for me, that's why I care. It could change how ice flows. Someone said freshwater over here. Where's the freshwater going? Into the ocean. And that's a big deal for ocean circulation. With the freshwater also comes micronutrients, carbon, iron, things like that. So you're talking about changing Southern Ocean circulation where we don't just have this constant flow of water going in, but we have these really focused streams being input. And then, of course, we care about the microbial activity because that'll drive how much carbon is being exported. It's also still a unique habitat for life. It's our best analog for extraterrestrial exploration. So on Mars, they found subglacial lakes. Europa and Enceladus, the icy moons of Jupiter and Saturn, are shells of ice with a liquid ocean beneath. We think there could be microbial life in there. And so these are interesting to a whole lot of people. One of the things I'm particularly interested in is typically the ocean beneath an ice shelf is really stratified. You have this cold layer of water beneath the ice sheet because it's in contact with ice, with warmer ocean water beneath it. And then if you have this focused discharge of fresh water, it can screw up that layering of the ocean and entrain the warm water up closer to the ice bed, and so that can change your melt rates. So there's a lot of reasons to be tracking these subglacial lakes and also exploring them and accessing them. You'll hear a lot about ice coring, so I just wanted to give you a slightly different flavor of a drilling experience. I'm sure, did you see pictures of kind of like a waste divide style ice core system where you have the big, whatever they call it? What's that called?
Disc drill.
Yeah, but what's the enclosure called?
Oh.
The arch. You have a big arch enclosing the entire thing, so there's no wind. It's this nice environment. Sure, it has to be cold because it's an ice core, but at least you're kind of isolated from the outside. For us, we're drilling an ice stream. We're using hot water, so this is a glorified hose with 200-degree Fahrenheit water. Any ideas why we have to use water to drill instead of a mechanical drill?
Avoid contaminants.
Avoid contaminants. We can't put these weird petrochemicals in the hole. We have to use hot water, and there's actually a whole sterilization system that goes along with this. We pasteurize the water, filter it, we send it through UV sterilization. And so if we're drilling with hot water, we have a lot less time with the hole open, and so this all has to be fast. So this entire camp, gigantic camp, 2 weeks. So the whole name of the game is we need to build as little infrastructure as possible to get the work we have to get done. And so that means we're outside. which sucks. And it especially sucks because we're taking samples, and you need this fine, delicate work with your fingers. So you're wearing nitrile gloves outside in Antarctica to do these tasks, and everything's dripping with water. It's a tough couple weeks, tough 2 weeks. So this is a sediment coring where we got that picture of the pebbles, and we get that mud. And there's also a whole host of dangers associated with this. That's a different risk profile entirely. This is a hole 1,200 meters down in the ice sheet. It's just sitting there. There are a lot of people going in and out of this area because the scientists, need to be doing the sampling. We don't just have the drillers at the drill site and then they pass the core over. And so things, we really need, as you always need to be in the field, you need to be aware of safety, but the risks are a lot higher. I mean, if someone forgets to put this metal covering on there, you have an open hole. And our holes are big, about a meter on top. So it's a very different experience than being in an ice core camp. Nope. So the hole will flow back in. So within a couple weeks, it'll be closed. There's still a lot of outstanding questions. I mean, we're only just starting to skim the surface of understanding these subglacial systems. Here's just the list that I came up with off the top of my head, but we don't even know how much water is in the system. So we know we have a model that tells us how much water we're producing, but some stored, some flows away. We have these lakes that are either filling or draining. We don't know what the water budget looks like on the entire continent. That's like one of those first order problems. We've only drilled 2 spots, and they're 50 miles away from each other. It's like taking a sample from New Orleans, going to Baton Rouge, and saying we know what the water system in North America looks like. Like, that's ridiculous. You would never say that. So we're just starting with all of these questions. With that, thank you. These are some of the funding agencies, NASA and NSF. I just put the logos of the projects up because if I put the actual institutions that worked on all of these problems, it would fill the entire slide. Thanks for listening. Happy to